Hello everyone, my name is Tanya and today I'm going to talk about our paper, Equi-explanation Maps, Concise and Informative Global Summary Explanations. This work has been done at UMass Amherst and is in collaboration with Professor Razieh Rahimi and Professor James Allan. Let us begin. The problem that we study in this work is relatively new. Let us assume that we have a binary classifier which chooses between different treatments based on patient features to cure heart disease. How does the model make decisions for different values of smoking and exercise? Since these are critical decisions, it is essential to verify model sanity. Existing methods of local and global explanations aren't good enough to rule out rogue instances for this problem. Let us assume that we have used a local explanation method for the same. We would have to sample thousands of instances from the region of interest and compute explanations for each of this. Even then, it doesn't guarantee that we would rule out the rogue instances. Let us assume we use global explanations for the same task. Global explanations are an approximate over all the instances in the feature space and hence would not point out anomalous behavior of a single instance. As a result, for these type of tasks, we need to look for explanations of varying granularity, which lies somewhere between local and global explanations. To solve this problem, we present Equi-explanation maps. Equi-explanation maps is a new data structure, a new explanation presentation format. It takes as input a classifier F, its explanation features E, an approximate data set on which F has been trained or will be tested, and an explanation granularity epsilon. Based on this, Equi-explanation map outputs a division of the convex hull of the dataset into Equi-explanation subspaces and additive feature attributions for each subspace. For example, let us assume we have a binary classifier with two features, feature 1 and feature 2. Equi-explanation maps divides the region of interest into three equi-explanation subspaces or regions, R1, R2, and R3. It gives corresponding feature attributions for each subspace, as shown below. Let us now look into how to generate equi-explanation maps. We propose a method emap, which is specifically optimized to generate equi-explanation maps. The emap architecture is as follows. We start with an approximate convex hull of the region of interest. We then use a divide and conquer based approach such that we first compute the coordinates of the hypercuboid formed by the convex hull. Then we heuristically keep recursively dividing the hypercuboids into subhypercuboids until the standard deviation of explanation vectors of the hypercuboid coordinates are less than epsilon. Once we receive a list of hypercuboids whose standard deviation of explanation vectors is each less than epsilon, we try to merge neighboring hypercuboids while keeping in mind the epsilon constraint. If a list of hypercuboids together have standard deviation less than epsilon, we term that as a subspace. A subspace can have one or more than one hypercuboids. We then compute the aggregated feature attribution or explanation for each subspace by doing a volume-wise aggregation based on each hypercuboid's volume. We then accumulate and present the hypercuboids subspaces and their feature attributions in a tabular representation, which is both concise as well as informative. Below, we have an explanation of an equi-explanation map. This particular equi-explanation map has three explanation features, age, cholesterol, and rest ECG, and four subspaces. Subspaces 1 and 3 have a single hypercuboid, whereas subspaces 2 and 4 have three hypercuboids consisting in the subspace. We have one feature attribution corresponding to each subspace. We see that if we have D explanation features, each hypercuboid can be represented using 2D coordinates, which represent the min and max of each hypercuboid. Next, we discuss some of the experiments we do to find out the effectiveness of equi-explanation maps in generating global summary explanations. We carry out experiments on two datasets, namely the UCI heart disease dataset and the PIMA Indian diabetes dataset. We compare against 4 other global explanation algorithms, namely SP-LIME, Guided LIME, SHAP, and Muse. Of these, the first 3 are additive feature attribution methods, whereas Muse is a rule-based if-then list-based mimic model method. We compare the algorithms on grounds of 3 evaluation metrics. First being interpretability, which is the multiplicative inverse of the information needed to present explanations. This is essentially the number of numbers which we present while presenting an explanation by a certain method. The next evaluation metric is fidelity. Fidelity is a common explanation evaluation metric in explainable AI and is the fraction of points for which the black box prediction agrees with the explanation model reconstructed prediction. The third metric is new and proposed by us and often overlooked by other explanation algorithms. Informativeness. Informativeness measures the average similarity between local and subspace explanation vectors in the region of interest. Next, we discuss the experimental results for our first set of experiments. We first compare the performance of the 4 explanation algorithms, feature attribution explanation algorithms on grounds of interpretability, fidelity, and informativeness on both datasets, the UCI heart disease dataset and the PIMA Indian diabetes dataset. What we observe is that Equi-explanation maps outperform the other 3 explanation algorithms on grounds of fidelity and informativeness on both datasets. However, it gives largely subpar performance on grounds of interpretability on both datasets. In our next set of experiments, we set the value of epsilon fixed at 0.6 and vary the underlying architecture of the model we are explaining. We consider 4 different underlying architectures: logistic regression, SVM, 3-layer MLP, and XGBoost classifier with epsilon fixed as 0.6 and generate Equi-explanation map explanations for each of the following. We then compare the performance of these Equi-explanation map explanations on different underlying architectures on grounds of interpretability, fidelity, and informativeness on both datasets. What we observe is that more complex the underlying architecture, lesser the value of interpretability, which means more is the number of subspaces generated by EMAP algorithm for the same fixed value of epsilon. So here, SVM and XGBoost classifier have the most complex underlying architectures and hence the least interpretability. We also carry out a user study to understand the real effectiveness in human understanding using Equi-explanation maps. We also conduct a user study to compare between Equi-explanation maps and rule-based mimic model-based methods, since it's not possible to compare this varying presentation formats quantitatively. So given here is a Muse explanation, which is a following list of if-then rules, and given below is the Equi-explanation map explanation for the same classifier. We ask volunteers who are all proficient in machine learning basics a variety of questions after being shown explanations of both formats. One of the first tasks we ask them to do is to predict the primary feature responsible for decision making. 72% of volunteers who are shown EMAP explanations get it right, as compared to only 32% of volunteers who are shown Muse explanations. We also asked them a plethora of other questions, including which method would give more compact explanations as the number of feature scales, which explanation presentation did they find more informative, and which explanation presentation did they find easier to understand. Volunteers claim that Equi-explanation maps outperforms if-then based mimic model methods on most of these metrics, especially as the number of explanation features increases. In conclusion, we proposed Equi-explanation maps, which is a new data format to generate compact and informative global explanations. We propose EMAP, which is a method to generate Equi-explanation maps. We introduce the metric of informativeness to evaluate explanations. We showed gains on grounds of informativeness and fidelity. We list a list of future works which would further improve this algorithm. The first would be an automatic method to compute epsilon value rather than leaving it on the user input. Another interesting HCI work would be better visualization for interpretable results in higher dimensions, since tables are also harder to read for dimensions greater than 5. Another future work would be to study the compactness-informativeness trade-off for global summaries in detail and reach a sweet spot between local and global explanations. Thank you, and please feel free to contact me for further questions.